So what I'd like to talk about is a few new directions we're taking software-defined networking from the traditional sort of large infrastructure data center approach to software-defined networking. And with this, I'm going to sort of wear two hats. One is De Novo Group, which is a nonprofit that I joined not too many months ago, and ICSI, which is sort of my research hat affiliated with the UC Berkeley SDN research group. So I'd like to start with set aside a little bit what the standard thoughts about the way SDN is both used today and is being considered to be used today, and look at a few areas where we think it could be used that it's not currently being used, and what are the things that SDN can provide. And specifically there, we're looking at De Novo Group for deploying and designing really new SDN solutions for rural networks. One of the main goals of De Novo Group right now is to try and increase access to the internet. And a lot of the places that we're trying to do this are places that management of networks can be a real problem. And so we're trying to figure out how can SDN, which has proved valuable in some places in data center networks, how can we use those same ideas or different ideas that are related to rural networking. And then on the flip side, sort of with a researcher hat on, I've been working with a number of people at UC Berkeley on doing SDN troubleshooting, because one of the things that I think most people know, as soon as you start examining SDN, it's a little troubling, at least from a traditional networking standpoint. You have a single controller, either logically or actually physically centralized, and now you're at risk potentially, right? You have one single point of failure, and this is all relying on somewhat untested, somewhat new architectures, new software. And so we've been looking into how do you troubleshoot these networks? How do you make sure that you get the bugs out of that SDN control software, because you really are relying on it. And so this is sort of the tools approach to thinking about SDN. And then finally, we've been thinking about how do we even redesign SDN as an architecture? What things were good about it, what things were sort of misguided, or things have evolved and now the circumstances have changed. And so considering what would a next generation SDN architecture look like, and what are some of the key features. And so I'm going to just touch really briefly on these, and then maybe we can have a discussion about some of them. So for SDN for rural networks, one of the big questions that we wanted to answer was, why don't WISPs, wireless internet service providers, why don't they scale? And I mean, these WISPs exist all over the US, all over the world, in all sorts of rural areas, and maybe some of you use them as your primary internet service provider. But typically they don't scale. They're not very big. They're usually one or two people running it, often come out of the local community, people who have some hardware expertise. They like climbing towers. They like playing with network gear. But usually it stops at that. Sometimes they get bigger, but usually they stay at that size. Everything is sort of done manually. It relies on one or two core people, and the enterprise lives and dies with that. And beyond that, they face a lot of different challenges in terms of operation, in terms of long-term financial sustainability. We wanted to understand why this is a problem, because our goal is to try and get internet access out there in places that don't have wireline infrastructure. And right now we're actually working on a couple deployments in Northern California to this end, to try and basically act as our own WISP, at least in the short term, and then hopefully hand it off down the road. And so we had a couple hypotheses about what is going on there, why WISPs aren't scaling, and maybe where SDN can help. And so one of those hypotheses is management complexity. Partly it's the complexity of managing a network, because you're dealing with every layer of the network stack, and networks have gotten complex enough that usually expertise is at a specific layer, right? Either somebody is a wireless expert and really understands, say, layer 1, layer 2. Sometimes you'll have somebody who has a lot of expertise in, say, network security and firewalling and managing middle boxes and things like that. It's rare that you find a single person that actually knows all of these things. And especially in a rural area where one person is doing everything, or two people are doing everything, that complexity is difficult to manage. And so we wanted to try and tackle this management complexity, and this seems like a natural place where SDN has proved itself in managing really large networks. And so if it can manage really large networks, why not manage smaller networks but have a lot of moving parts? Another is infrastructure cost, and this one, SDN may or may not be able to mitigate it, but it's certainly a challenge that rural networks have to face all the time. The infrastructure itself that they have to put up, wireless towers and these sorts of things, they just cost a lot of money. Upstream bandwidth is really scarce, and if it exists at all, the incumbents are happy to charge a lot of money. And that brings us to incumbent challenges, which again is not something that's easy to deal with, but we think there might be an avenue where SDN can even help dealing with incumbents that are, they hold all the keys to the internet in some rural region. There will only be one incumbent ISP, maybe two, and a rural WISP that wants to provide service, they have to go to that incumbent to get internet, upstream bandwidth. So trying to balance all of these challenges that WISPs are dealing with, we thought there are three primary things that SDN can bring to the table. So one is active monitoring. We were kind of surprised, and this seems like a no-brainer, right? Active monitoring is one of the oldest things in networking. Everyone monitors their networks, but we've been finding, to our surprise, that really a lot of the WISPs don't really actively monitor their networks. And it's just there's too many things to do. With one or two people, you can't be watching your network. And so only if something fails catastrophically do they ever go and look into the various dashboards they've set up, plug together 10 different open source tools and see what's going on. And we think that providing a single unified interface for monitoring their network, that every piece of hardware anywhere in their network is feeding into the single controller and single view, and hook this into other automated systems that can, say, dispatch people to go and fix hardware. This is a pretty obvious win. And this isn't unique to SDN, it's just that perhaps this would make it easier because we can unify things. Another, which is again not new, but again, SDN can provide some flexibility, is remote management. We've talked to a number of WISPs, actually here in even Sonoma County, and we found that they're often driving through small mountain roads to go fix some piece of hardware. There's no remote management support for most of the hardware they buy. Partly it's because it's off the shelf, the cheapest wireless gear that they can get that can do directional Wi-Fi. There's just no good software support for these. They're running whatever custom vendor software, and usually they don't flash them with OpenWRT or anything like that, put their own software on it. And so what we're planning on doing, and what we are doing right now, is building our own software tools that will go on these commodity devices, these cheap directional Wi-Fi gear that WISPs are using and that we are using ourselves. And so then we can do remote management, test out our systems, revise them, and then potentially roll them out to other WISPs that could use it. And finally, this last piece is actually where we may be able to break the chokehold that incumbents have, which is that we can use SDN to decouple services. So just as I was mentioning earlier, the fact that there's expertise at a few layers of the network stack means that perhaps the folks that like climbing towers and driving on the mountain roads to set up wireless gear, they may not want to be sitting there managing QoS policy, right? It's a different set of expertise, a different set of interests. And what we might be able to do here, and we're going to be trying this out ourselves to see if it's really effective from a business standpoint and from a networking standpoint, is decouple the service of running a rural wireless network from the IP level service that runs on top of it. And so this is often talked about as network virtualization, right? There's a lot of terminology that gets used in the SDN space for this. But the bottom line is that no longer does a local regional operator have to compete with the incumbent for customers. The incumbent, whatever large ISP, can provide IP level service. They can handle the billing, the customer service, all of these different things. And the local WISP can provide infrastructure service and actually deploy the infrastructure and manage it. And you can have a single SDN system that handles both sides of these. So this is a picture of where we're going with this deployment, and we think it can have some potential benefits. There are no software tools out there that actually bring all the features together that we need, and so we're actually writing our own SDN controller to do this, and it will be open source in time as we've worked out the kinks and figured out exactly what features we need. Now, so this sort of brings me to the other aspects, some more researchy aspects of my work and my interests. And this is in collaboration with the SDN research group at UC Berkeley. What happens if the controller fails? Right, this is a perennial problem in SDN. And before I joined De Novo Group and came back to research, I was at Google doing SDN within Google's networks and redesigning the routing system. And you have a single controller which is handling all of these and perhaps many more aspects of your network. And there's a lot of risk there, and how do you mitigate that risk? And part of the difficulty is not just that it's a complex distributed software system that you're building, but that it is really brand new software. I mean, the commercial controllers, as I can testify firsthand, have just as many bugs as open source controllers that are out there. This is just a fundamental problem of software. And while it does help that it's a single piece of software rather than a bunch of distributed nodes managing a distributed protocol, we need some support for troubleshooting, and there hasn't been too much to date. And so one of the projects we have ongoing, and there's open source code on this I can point you to, is a system for SDN troubleshooting. How do you make sure that the controller, when there is a problem, you can figure out what went wrong? And this is both when you're doing testing of an SDN system beforehand, before deploying it, but also while it's actually running, there's some failure that occurs. How do you find where the bug was? Right? What you might get, you being an engineer working on the system, somebody who's managing or administering the system, you might have a trace. The trace will say, this link went down, then this packet came into the controller, which told you something about some advertisement from some other protocol. There were some internal state transitions, maybe one of your replicated controllers failed. So you have a sequence of events that happen, but you have all these different nodes that are feeding in information constantly. How do you know which of those were even relevant to the failure, which may be something like there was a loop in your network, or there was a black hole, or some access control policy got violated, right? There's lots of different sort of invariants that you want to maintain. One of those might have been violated. How do you know which of these events was even relevant? You might have hundreds or thousands of events to look through, huge trace, maybe even days long. And so the objective of this tool is to do trace reduction is the first step. And what we're trying to do is trying to figure out what is the minimal set of these input events in the network that are causally related to the failure that you saw, that invariant failure. Say you saw a routing loop. Which of the events was actually related to the routing loop, and which of them have no relationship, they just happen to have happened at the same time, right? Most likely, there's only a small number of those events that are truly related to the failure, but you have all sorts of other stuff to sift through, and once it gets too large, it's just impossible to figure out which of those you want to try to find the bug. And so what we have is a system that does automated trace reduction, and so it takes in a series of actual events, and we've done this with 5 open source controllers written across 4 different languages, so it's agnostic to the controller and to the language the controller was written in. And it does a technique that's from the programming languages community called delta debugging. And the idea is that it's really simple, sort of divide and conquer. Chops your trace in half, and then it tries to replay what happened in the first half and the second half in a controlled environment. And then it says, did I reproduce the bug in one of those halves? If it only appeared in one half, you know the other half of the trace is irrelevant, and then you can continue subdividing. But you might find that both halves have some amount that's relevant, right? So there's several techniques in delta debugging to try and whittle down the trace, and we found that you can reduce traces sometimes 95% in terms of their length. And then it returns to you what we call the minimal causal sequence. It may not be truly minimal, but it's as minimal as this tool can get it. Then you hand that to the engineer or the person who's doing the network debugging and say, this is the sequence of events that will trigger this failure in your network, this routing loop, this black hole, this access control policy violation. And then they can go from there, right? At that point is a standard debugging task, but a much easier one. And so we've used this actually to find a number of bugs in open source controllers that were not known before. And we're hoping to use this in the de novo group work that I was talking about earlier. Now, one of the challenges here is that we have to mitigate non-determinism, because when you replay something, you're now trying to, in a controlled environment, replay something that was non-deterministic to begin with. And so we have a bag of heuristics, and there are too many to list, on how to mitigate the non-determinism. The good news is that even if the non-determinism is out of control in your network, the worst case scenario is that we give you a slightly longer minimal causal sequence, because we're not able to tell which half of the trace, when we're subdividing it, an error occurred. And so we say, well, it could have been in both, so we're going to return a longer subsequence, and then you as the engineer have to debug it. But this is one of the main challenges in achieving this. So that's sort of the two, I guess, more concrete things that we're looking into. And then a slightly, I guess we could say, abstract or architectural thing that we've been discussing is right now what we're broadly calling SDN v2, trying to think what would the next generation of SDN look like, and what are the lessons we can learn from SDN deployments that have happened to date. And part of this starts with three, there's actually a fourth which we're still formulating about virtualization, 3 observations about what SDN v1 looked like. And so one of the assumptions was we had a simple data plane, that your data plane consists of switches or routers that are forwarding packets, and their job is to do the things that you could express using OpenFlow or something like OpenFlow. That you had relatively homogeneous routers, and that you were using hardware forwarding, and so that you were using this interface to talk to the network and tell the switches, these are the things, we know that you only can do these actions, whatever, say, OpenFlow can express. Program those, and then do the actual data plane forwarding in hardware. What we've been discussing and sort of using empirical results about the way networks are managed and so on to reconsider each of these. So really, most networks actually don't have simple data planes, right? There's extremely complex data planes. Most packets are being touched by many middle boxes, and these middle boxes do all sorts of different things. They all don't coordinate their policies. And so maybe the assumption that SDN made about simple data planes wasn't valid. And so how do we address that? The network isn't homogeneous. Most carrier networks, and perhaps maybe a lot of networks that aren't even larger ISPs, have a core edge split. The core is treated somewhat like a fabric, right? The packets come in, you use some lower layer technology to get the packet through the core and then out the edge again. And so how do we embody that in SDN? Does that change the way we think about the way we design the SDN system? And finally, we're getting to a point where software forwarding is actually feasible. Not just feasible for some middle boxes, or we think it's actually to the point where you can do data center networking all in software. We're almost at that point. And so what are the implications of being able to do software forwarding on the way that you design the network? One of the obvious ones is that you no longer constrained or no longer need to be constrained by something like OpenFlow, which is trying to express things that only some limited set of hardware functionality can support, right? You could imagine an interface that's saying you can basically do anything you want within this x86-based VM. And if you want to write an application that runs in the network, in some point in the network controller will handle where that gets deployed, say some sort of middle box service, and then you hand the VM software to the network. It runs someplace and processes packets however you need it to. You don't have to be constrained by the existing interfaces. And so we've designed sort of prototypes for each of these and a coherent system that embodies this architecture. Whenever you're doing architectural work, this is something that's going to take a lot of iteration and refinement, and the prototype will never actually become the real system. The goal is to try out some of these new ideas for SDN architectures and then see if they're useful. And one of the places that we're using this is the first deployment that I was talking about, the rural wireless deployment. We're following the model of software forwarding because there we have the benefit of really low bandwidth networks, so software forwarding is a no-brainer. Core edge split, again, because we have a core infrastructure of point-to-point links, and then edge nodes, which are really the end users' access points and what the CPEs, the customer premises equipment. And the complex data plane, we don't have that much complexity at the moment, but perhaps if we start offering other services that people need in these rural areas, the data plane might get more complex. So these are sort of the three things that I'm working on that I think are somewhat related, maybe relevant to what you all are doing, but I'd be happy to take questions.
Just as a clarification, you talk about SDN v2. Is that just rethinking the concept a little bit, or coming up with new technology? Because I think most of the items that you mentioned as what would be, what you would consider the second gen SDN are not necessarily new things. I mean, it's already being considered with the current V1 version of software-defined networking. It's just getting there by actually developing the necessary software to do the steering to actually be able to implement something like that.
Yeah, so it's a little bit of both. I guess. Can I repeat the question? Sure. Yeah. So I don't want to butcher. My interpretation of the question is, are we developing new architecture or new technology? Because some of the technology is already out there in sort of iterations of SDN v1 broadly construed. Is that roughly? And I agree. A lot of these basic, a lot of the pieces of technology individually, software forwarding has existed for a long time, obviously. It's just a question of, was it feasible enough to integrate it into the overall architecture, to expect that when you deploy something, you have complete flexibility as to what you do with the packets, rather than what OpenFlow enables you to do. Things are sort of proceeding on a parallel track, for sure. That, and our hope is actually that we converge, that our architectural thinking from that angle converges with what the underlying technology provides. And so a lot of what we're focusing on is not, say, improving software forwarding, because we expect it's going to get there on its own, but rather, what are the programming APIs that you actually need so that when you're writing a controller or writing an application that's talking to a controller, you can flexibly say, I want to deploy this piece of software and then just have it be running out there.
So it's more an approach of new concepts as opposed to new.
Yeah, definitely. Yeah, so the SDN v2 is a little more on the abstract end of the research. Yep. Thanks.
So Katya, it turns out, was across the hall and was told that the session was running late, so she has joined us. While she's coming up, I will introduce her. Katia Obraczka is a professor at UC Santa Cruz in the Jack Baskin School of Engineering. Her research and teaching interests include computer networks, distributed systems, information systems, and operating systems. I will help you. Thank you. I'm going to plug her in and get her started here. Maybe to flip it. Yeah, the other way.
Great.
And you're sharing, not mirroring.
I think I just need to do this. No?
Go to settings.
Systems preferences,
And
displays.
and arrangement.
Mirror?
Yeah, there you go.
Oh,
There you
yes.
go. And now you can go back to PowerPoint. And there you go.
Oops. Oh, I did it. Why it's doing that? It's over there, no? It doesn't like it. You think it's the resolution, maybe?
No, that should be presenting now.
Oh, there you go.
No, that's the
Then
wrong
when-
one.
But then when you,
Hmm. Not good.
maybe the resolution.
I'm gonna try, because it's
See,
doing
because it's showing part of the screen there, which is kind of weird.
Okay, so do we need to change? It's saying scale.
It's
There's-
very fine, but
Yeah. So I don't know what resolution we need to do.
yeah. See, it's good. I don't know exactly why it's doing that. I don't know why it doesn't like it.
What happens if we go back to mirroring now with that resolution? Because now that they match, the problem with VGA stuff.
Arrangements. Oh,
I'm gonna try it. It should just work that way.
I don't know why it's getting this. Oh, there you go. It showed up.
Oh, we're mirroring, yeah, just to go full window with that.
Oh,
There's something it's not pushing, so let's do this. Okay, we're faking it, folks.
don't do slideshow
Yeah, it won't take. PowerPoint won't take over the projector.
for some reason. So we'll just go that way.
Yes.
I use it all the
Yeah.
time, so I don't know. All right, sorry about that. Hopefully, this will be fine. Okay, so I came here to talk a little bit about the stuff we do at UC Santa Cruz with SDN. I wasn't really sure what kind of audience I was gonna get, so I have some slides about SDN just in case, but we can skip that. Oh, I need to go this way. So some of this work is part of a collaboration we have with some people at INRIA in France and also at University of São Paulo in Brazil. And If you need more info, there's a link over there that is not very readable, but I can send it to you if you'd like. No, right. So what I would like to do is go over this sort of outline here, where I'm going to give you our motivation for working on this topic. And basically, our motivation is coming from our vision of the Internet of the future. A brief overview of SDN, but we can skip that. And then we can talk a little bit about the work we do in trying to distribute the SDN original paradigm. A little bit about our current work, and then, of course, some conclusions. So if you think about how the Internet is sort of evolving, I kind of see it in sort of 5 phases. And this is actually, this picture I stole from someone, so the credit is over there. So when, in the beginning, we have very few machines, as you probably all know. Then, of course, things started to grow, especially motivated by things like the World Wide Web, so doing resource discovery. And then phase 3 was connecting people like wirelessly. And then social networks came. And finally, we are sort of in stage 5, where we have things like content-centric networking, Internet of Things, and all that good stuff, which, of course, all of this places a lot of problems on the current infrastructure. And so how do we make everything scale? Where do we go from here is kind of the question we are trying to answer. So what is the future of the Internet? And of course, if you talk to different people, you're going to get different answers. Our answer is that the Internet is going to become, of course, bigger and bigger, but also more diverse, more heterogeneous, and more decentralized. Okay, so we're going to have things like sensor networks. We're going to have things like ad hoc networks, vehicular networks, all of these sort of non-traditional networks attaching to the Internet. If you will, interplanetary Internet is also something that people are talking about. So, of course, many challenges out there. Scalability is an obvious one, heterogeneity in terms of not only devices, but also the underlying network technology and the services that are going to be provided. And, of course, increasingly autonomy, increasingly more administrative decentralization. So at UC Santa Cruz, my group, my research group, our work is, again, motivated by this vision of the future Internet. And what we do is basically design and develop, implement, deploy protocols with that vision in mind. So we sort of departed on this journey trying to think about how SDN could help us because of, and again, I'm not going to bore you with that because probably, this is redundant, but the basic idea again behind SDN is the separation between the control and the data planes, and that means that the network infrastructure is out there, and then you don't and no intelligence there, and all the intelligence is sort of sucked and put in this entity called the controller. So this idea of a network operating system, sort of similar to operating systems in regular computers, where you have the network out there and then you manage it from this controller. entity, and where the controller then provides some basic services, network management, topology management, and then you can develop, some core applications. Not even my pointer wants to work. Anyway, some core applications on top of that, and then more elaborate or sophisticated applications on top of that. So this is, again, a standard picture where you have the communication between the controller and the forwarding hardware, and then you also have what they call the northbound interface, where you communicate between the controller and higher or more sophisticated applications that you can implement on top of the controllers. So just a quick overview again. The idea of programmable networks is not new. It has been around for a while. Way back when, I'm not sure if you guys remember, in the mid-90s, DARPA came up with this idea of active networks that everybody hated, and it never went anywhere, right? So it's been here for a while, and there were other attempts at this programmable networking idea. And if you are interested, we're just publishing a survey on SDN, and if you want, I can, the pointer is there, but I can send it to you as well. But many challenges. It has attracted a lot of attention from both research and industry. Lots of work on the forwarding plane, trying to make it scalable. Lots of work on the control plane, also trying to address scalability, fault tolerance, as we talked about before. And so lots of interesting work trying to address all these very hard questions. So again, in the control plane, a lot of work trying to scale the controller by either doing flow aggregation or looking at reactive versus proactive policies, etc. Again, I'm just going through this very quickly because I don't know how interesting that is for you guys. From our point of view, what we are trying to do is to use SDN, again, to think about these heterogeneous, administratively decentralized networks. But then you're going to say, well, but there's a problem here, right? SDN is inherently centralized. How you're going to do that? So that's exactly what we're trying to do. We're trying to propose ways to do distribution of the SDN control plane so that we can tackle these autonomous or administratively decentralized internets. So this we're calling our approach DSDN for decentralized SDN, or maybe D squared SDN for distributed decentralized SDN. There has been a lot of work on physically decentralizing SDN, like replicating the control and then trying to make them consistent, these replicas, these controller replicas, consistent with one another. But what we are trying to do is actually decentralize logically. So you can have different, completely independent controllers out there that will probably have to communicate to achieve some function. Okay, so this control distribution will then be able to enable these functions that we see are necessary in these internets of the future, like, for example, what we're calling network capacity sharing, which I'll discuss a little bit with you about what we did. And of course, being able to do fault tolerance and load balancing on the control plane. So again, lots of interesting work out there on controller decentralization. And here are some pointers where people have proposed controller-to-controller communication, given that it hasn't been defined in the original SDN paradigm. Okay, so this is something that we are also working on. So these are pointers for work that has been done in terms of physically decentralizing the control plane. So for example, the work by the people that created Onyx and Hyperflow have looked at control plane decentralization. But in these cases, they are, again, logically centralized but physically decentralized. So they enable communication among these replicas, but they try to make sure that they are consistent. There are other approaches out there like Condu and Disco, and they are, these are slowly trying to move on to the idea of logical decentralization. Our approach, again, which we call distributed SDN or decentralized SDN, is to look at decentralization of control by creating this hierarchy of controllers. And the controllers in this hierarchy, they may have different functions. Depending on where they are in the network, they may be doing different things, and they will likely have to communicate with one another. So for example, if you are in a vehicular network or in a network that is not connected to the main infrastructure all the time, the controller that controls that network is not necessarily going to be connected or being able to connect to the main controller at all times. So there has to be some autonomy between these two entities. So what we see is that there is going to be the concept of these main controllers that will talk to the secondary controllers, and depending on where they are, they will have to function independently. And these controllers may have different functions. So the main controller may only want to delegate, so we have this concept of delegation of control to the secondary controllers, but they don't want to delegate all the functions, they want to delegate just a subset of the functions to these secondary controllers. And of course, there opens a lot of interesting security problems, right? So secure communication between the controllers is something that we are looking at, and basically the framework that we are proposing has security embedded in it, so that we can create these secure channels automatically. And also we are developing features that will allow us to do fault detection and recovery as well as load balancing. I just saw the 5-minute sign, and so I'm going to rush here a little bit. So this is a use case that we have developed, and we are calling it network capacity sharing, which is the ability of users to share network capacity, and where users are not necessarily covered by the infrastructure. So for example, in this case, we have a scenario where we have a user, Alice, who is roaming, and for some reason she's not able to connect to the internet. So what she does is that she talks to Bob, which is another user, and Bob works as a gateway for Alice to access the infrastructure, the internet, through him. There is some handshaking between Alice and Bob, and then Bob talks to the main controller. So in this particular situation, we are assuming that Bob and the main controller are connected. Okay, so we haven't gone the ad hoc network way yet. And we're also assuming that Alice is one user out there, but in fact, you could have a network of users that are connected amongst themselves, but are disconnected from the internet and are using Bob or any other user as a gateway to connect to the internet. Okay, so this is the scenario that we're calling capacity sharing that we're using SDN to implement, where, let me just skip. So this is a picture of our implementation where we have these software switches running on these devices, and then we have a secure channel that is established between Alice and Bob, and then between Bob and the controller, and that way this handshake is done, and finally Alice is able to connect to the infrastructure through Bob. And we also have implemented a handover feature where if another gateway comes into play, in this case Charlie, then Alice can decide to switch over to Charlie and connect through Charlie to the internet. For example, looking at QoS questions or doing some sort of load balancing between Charlie and Bob. Okay, so this is again ongoing work. We've been developing this using public domain software, of course, and so these are some of the things that we've been doing. And in conclusion, we've been kind of playing with SDN as an enabling technology for the internet of the future, and again looking at how we can extend the original paradigm to a decentralized control paradigm, so that we can enable SDN to work on these highly heterogeneous and decentralized internets. So that is it. And oh, I'm sorry, the links. Well, there's my email address and the link to my lab, in case you are interested in taking a look at some of these publications. But you can send me an email, and I'll be happy to send the links to you. Thank you. Questions? Hey, Jim. Not from you.
Anyone but Jim.
You develop address translation as part of your SDN model in order to allow clients to hop from gateway to gateway?
Yeah, yeah. So right now we do, so the gateway is doing that for us. Great. Thank you.
Thank you, Katya.
Thanks.